Okay guys, so let's start. So first of all, I would like to thank you all for joining, and just to tell about this webinar. So I was taking an challenge for 30 days to improve speaking skills. So it was called Speak Like a Champ, and this is the final task for it to conduct a webinar. So as I already told, I am conducting the webinar on binary search, and we are not just going to focus on binary search on the numbers in a sorted array. We are going to unlock the true power of binary search. Okay, so let's get started, and we will start with the basic intro of binary search just to revise. So let me know if my draw board is visible. Let me know if my screen is visible. Should be visible. Okay, so just to clear the basics, so in binary search we basically have a sorted array, let's say like this, where the elements are in increasing or decreasing order. Let's assume for now they are in increasing order, and we want to find an element x, that if it is there in the array or not. So one thing we can do is we can just traverse from left to right and see if x matches any of the elements, but that would be linear time, like it will take n operations since the array size is n. So instead of that, we have a better algorithm, that is binary search, which will like find it in order of log n time. And how does it do that? So first we check if the middle element is same. So we will check n by 2 element. If it is greater, just a minute. We are just brushing up the binary search. So we will see if the middle element is equal to the search, the target element x. If it is not, then let's say if the middle element is am, and if it is less than x, then we have to search on the right side. If it is greater than x, then we have to search x on the left side. So essentially now the array size that we want to search on has halved, right? Now we are only working with n by 2 sized array, and this way we will keep on decreasing the array size again and again by dividing it by 2. So at a point we will just reach the condition where there is only one element. So then in that case we can say that n by 2 to the power k, where k is the number of iterations that we took, has become 1 because we are constantly dividing the array size by 2. So we can say that n is it's 1. So we can say that n is approximately 2 to the power k, which means k is log to n. That's why this algorithm will take order of log n time. Now that's a trivial example, and we already know how to write a code for that. Like just a minute, let me clear. So we already know how to write a code for that. Let's say we have the left bound 0 and the right bound, that is n minus 1, assuming 0 indexed array. So we will just do while L is less than or equal to R, we will calculate mid is equal to L plus R by 2, and we will see if the middle element am is equal to the target then return the current position, so that is m. Else if am is less than x, then we have to search on the right side. So we will do left is equal to m plus 1. Now the left bound is one position ahead of the mid, because mid we know that it is already less than x and the array is sorted in increasing order, and otherwise the only condition.
Whatever you are writing, your screen is not fully visible while you are writing at the moment. Yeah, now it's
Thank you. Yeah. So the only other case left is when and this case will be for am is greater than x. So in this case, just a minute. So in this case, we can say that the array is sorted again. So we will just push the left boundary to mid minus 1. So sorry, the right boundary to mid minus 1. So r is equal to m minus 1. And yeah, if this condition is violated, the l less than equal to r, then we know that the element is not present. That's why we will just return null or not present, something like that. Okay, and yeah, this is the trivial code that we know, and this is the trivial use case for binary search that we know. But the binary search is not just limited to this. We can explore more problems with binary search, and like binary search is very powerful, and let's explore the problems directly. You will understand. Yeah, first of all, before that, I would like to tell you when we can apply binary search. So let's say we have a function which is monotonous. And what is a monotonous function? Let's say this is the graph of function. So f of y is equal to f of x. And a monotonous function is the function that either keeps on continuously increasing or continuously decreasing for the given range of inputs. Okay. So if we have a function like this, only then we can say that if certain condition is satisfied for this current yi, if certain condition is satisfied by function y, like we will, not a condition, let's say we can directly say that if x1 is less than x2, then is less than or equal to x2, then we can say that y1 is less than or equal to y2, and y1 and y2 are functions of x1 and x2. So in this case we can apply binary search, because we know that, let's say this is x1 and this is x2. So if we are somewhere around here and our target to search was function of x1, and at this point we will know that the function of whatever this value is, let's say xi, we'll know that this is greater than f of x1 that we were searching. So we will still go to the left, and analogous for the decreasing case. So this is the thing to keep in mind, that we can apply binary search only when the target function or the function that we are dealing with is monotonous, either increasing or decreasing. So let's look at an example. So here is the problem statement. So we have a factory which has n machines, and the goal is to make t products. Okay, and each machine can be simultaneously used. So So there's no condition that at one time you can only use one machine. You can use all the machines at the same time. So you need to find out the time, the shortest time in which you can make T products. So any guesses on this? Like any naive algorithm that you can think of for this problem? You can type in the chat box, or you can directly unmute and speak. Anyone wants to volunteer? I'll state the problem statement again, that we have n machines. Each machine takes some time that we know to create a product, and we have to create T products, and we want to know the shortest time that is needed to create the T products. Given that we can use all machines simultaneously.
Can you show the constraints?
Constraints? Yeah. So did you guys understand the problem statement?
Yeah, I think so. Basically, we are given n machines each, and we are given the time each machine takes to create one product.
Yes.
And we want to create T products, and we can use all the machines simultaneously if you want.
Yes.
Right? So in the explanation, maybe explanation would be more helpful.
So we have like 3 machines, and each machine takes 3, 2 and 5 units of time, and we want to make 7 products. So the minimum time that we will need to make 7 products is 8. How? So machine 1 will make 2 products, and it will take 6 units of time. Machine 2 will make 4 products, which will take 8 units of time. So that's total 6 products till now. And the machine 3 will make 1 product in 5 units of time, so that's total 7 products. And the maximum time was taken by machine 2, so it's 8 units of total time, and all machines were running simultaneously.
I think if one observation is here is if we can make, let's say, T products in 10 minutes, then we would be able to make T products in 12 minutes or 15 minutes.
Right, right. So that's the way to go. Exactly. So remember the monotonous function that I told. Can you relate it somehow with this problem? And whatever you said right now is exactly the monotonous function. Let's say the function returns true if we can create how much was T was the number of products, right? So
yes.
And let's say the function returns true if we can create T products, at least T products in X unit of time. Okay? Just a minute.
Okay.
So we can say that if T products can be created in, if T is possible in I time, I units of time, can we say that greater than equal to T products are still possible in I plus 1 time? You can say it, right? Because we know that you can create t products in I itself. So I plus 1 means more time. So we may be able to produce more than t products, but at least t products is definitely guaranteed, right? So this function is monotonous, like not just monotonous. We can say, sorry, monotonous only. So this would look something like false for some time and then immediately true for some time. So it's a monotonous function. It keeps on increasing or it is same, right? So we will just binary search on the time. We will just binary search on the answer, right? Like we will just query if in the given amount x can we make at least t products. If we are able to make t products, so I will write a pseudocode. Can we make t products in x units of time. So if this returns true, then what are we going to do? Any guesses? Let's say current bounds where L is equal to 0 and R is equal to the maximum time, that is, let's say something like int max, just a minute, let's see the constraints. T is 10 power 9 and AI is also 10 power 9, so it's almost, you mean in 10 power 18 we can make all products. So let's say R is 10 to the power 18. So this was the initial bound, and now we have this what was I saying? If we can make t products in x unit of time, then what are we going to do? Assume x is the mid that we calculated, m is equal to L plus R by 2. Any guesses?
I think here we can move the right boundary, right? Because now we know that at least we can make till here. So this is the current best thing that we know, and maybe we can move towards the smaller m.
Right. So we'll just set.
Since we have to minimize.
Yeah, correct. So we'll just set right is equal to mid minus 1, because we know that we are able to make it in mid. So let's see if we can make it in mid minus 1. We can make it in time less than or equal to mid minus 1, and also we will just update the answer is equal to m, and else we know that we cannot make it, so we need to push the left bound. So we will just do L is equal to m plus 1, that is mid plus 1. Now this answer will keep on being overwritten until we find a proper the perfect value of m. That is the answer, right? So that's it. This non-trivial problem actually turned out to be a binary search problem. Interesting, right? Should we move to the next problem, or do you want any more discussion? Do you have any question about this? No questions, so let's move to the next problem. So this is a good one. Like, you are given an array of n integers, and like at every second the array is shrinked. So by shrinking I mean like at the first second A0 will become the GCD of A0 and A1, A2 will become the GCD of A2 and A3, like that. Okay, so at every iteration the size decreases by 1, and the current element, like at the ith iteration, the current element will be the GCD of the I elements from that position in the initial array. Okay, so you want to find out, like, in what time it the array will become such that all elements are equal. Like, we want to make all elements equal, and at what time will this condition happen. And you can also assume that you are given a data structure that can compute, like, for the given array and a given index, what is the GCD of I elements from the current element. So just a minute, I will extend it over here. And first we'll go through the example. So the array is 16, 24, 10, 5. Yeah, it's already there. Okay. So the array is 16, 24, 10, 5, and in the next second it will become the GCD of these two, the GCD of next two and next two. So it will become 8251, and in the next step it will become sorry, there's one step after it becomes 8251, and after that it will become 211, and in the next step I'll write in the forward. So this is the current array. So after next step it will become the GCD of these two is 8. These two is, how much is the GCD of 24 and 10? I think 2, and 10 and 5 is 1. So in the next step it becomes this array, and in the next step it will become 2, 1. So it's one step, it's second step, and in the third step it will become 1. So any array will definitely become either 1 or the GCD of whole array. What you are saying?
GCD of this 10 and 5 is 5.
Oh, sorry. Okay. And GCD of,
I think they have written that we are kind of considering the array rotated. That is why I think in the samples it was even 8251. So 5 and 16 GCD is 1.
Okay. Just a minute, I read it wrong. So the GCD of 5 and 16 is 1. So we know that if the array has a common GCD, then at some time all elements will become equal to that GCD, and if not, like, the common GCD is always 1, right? So at some time it will become 1 or the GCD of all array elements. But now let's say you are given a data structure. For answering this, by the way, so at this time in one operation it becomes this, in second it becomes the GCD of 8 and 2 is 2, it's 1, and 1 and 8 is also 1, and in the third step it will become 1 and all these are 1. So it takes 3 steps to make all the array elements equal. But now you have access to a data structure, let's say, that allows you to query, that allows you to ask queries of form qi and length, that will return you the GCD of array elements I plus 1, I plus 2 to I plus L minus 1, and assume these are also rotated. So let's assume that you have access to this data structure. Now can you use binary search somehow along with this data structure that allows you to query it in, let's say, log n time, log L time, and L is at most n, so just we can say log n. So
this query function will return the GCD from I till I plus L minus 1, right?
yes,
All the elements GCD.
yeah. You can, like, for some hack you can try, like, you will just append this array back to itself, 16, 24, 10, 5, and 16, 24, 10, 5. So now you can say that it will return the GCD of this element. So yeah, you can use any hack to achieve this sorted rotated thing, but you have this access to this data structure. Now just focus on how will you use binary search to find out the minimum time in which this will become equal, all the array elements will become equal. Any guesses? Or should I continue with solution?
So if we have a given time t, for example, we could potentially look at how we can calculate the state of the array for that time.
Yes.
So if you have t equal to 2, for example, if you want to figure out what should be the state of the array, will it be 1 1 1 1 or not 1 1 1 1?
For t equal to 2, it will be 2 1 1 1, like this.
Right. So the direction that I was thinking is maybe we can finally search on the number of nodes.
Right. And why can we do that? Because once the array elements become equal, the GCD will always be same. Right? So
Yeah, so like if let's say we have processed 5 more and the GCD has become all 1, then we know that if we repeat for 7 or 10 moves, then the GCD will remain 1.
right.
And I also agree with this approach.
And we also know that after n moves, the array will definitely become 1 1 1 1 or the GCD of whole array, because we will be taking the GCD of all the n elements at each index, right? So we know that the left bound is 0 for us and the right bound is n. Now we also know that if at some time the array becomes equal, then for all the time after that it will remain equal till n steps, right? So that's why if let's say we have a function equal at some time t, if we know that this array has become equal at t, we will just set answer is equal to t, and we know that it's equal at t, so we will have to check in the lower bound, right, like till t. So we will decrease the right boundary to t minus 1. Otherwise, if it's not equal, then we know that till this time it's not equal, hence we will have to push the right boundary. We will do right is equal, sorry, we will have to push the left boundary. We will do left is equal to t plus 1, and this will eventually override the answer to the final expected one. But one more thing is left, that is, how are you going to check if it is equal? Remember, you have this function for your help. You have this function for your help. By the way, it's beyond the scope of data, the binary search, but yeah, just a fun exercise.
So for checking equal, like we are given this t, so we know that the GCD of I to I plus t minus 1 elements will be considered as ith element, right?
Yes, sir.
Because they are having t move.
What were you saying?
No, I was thinking like for each element, I think we need to. So for each element, at the time t, we have taken the GCD of I to I plus t minus 1, right? Because in each time we take the GCD of t consecutive elements.
Right.
So
Yeah,
not sure,
it's,
like for each element we have to do this, right?
yeah, but this loop, the binary search loop, it will run only log n times. So this will take log n. It will be in a loop while L is less than or equal to R, to find mid, P is equal to mid, and yeah, this will take log n time. Now we want to minimize the time for equal function. So simply what we can do is we can do it in n log n, because this query takes log n time, so it takes log n, and for each index we will simply see if let's say we just have this value v is equal to query of index 0 till t elements, since t was the query, and t minus 1, sorry, t elements, so we are using 0 indexed. So we will just check if all the elements, like for I is equal to 0 to I plus t minus 1 to, sorry, n, what is that, I plus t is less than or equal to, is less than n. For I is equal to 0 to this condition is satisfied, we will just check if this query of I to of t plus, sorry, t minus 1 is less than, no, it's equal to, it's equal to v or not. If it's not equal to v, we will simply return false, otherwise we will return true. So it will take n log n time, right? So n queries, at most n queries, each query takes log n time, and this equal function will take n log n time, and the binary search is taking extra log n, so it's n log square n. Okay, yeah, this was an interesting problem, and let's see one more problem, and then we can discuss something special, that is parallel binary search. This is done. We'll quickly go over this problem. So we have a road network consisting of n junctions and m one-way roads, with each road leading a number leading from a lower numbered junction to a higher numbered junction, and each road has a number. Your task is to find a junction, a path from junction 1 to junction n, consisting of at most d edges on the maximum number of on which the maximum number of corresponding maximum of the numbers corresponding to the edges is minimum possible. So you have a graph with n nodes and m edges, and you want and that's a weighted graph, and you want to find a path from 1 to n such that it contains at most d edges, and you want to know the let's say the weight of that path is the maximum weight of all the edges in that path, and you want to minimize this. So how are you going to solve this? So I will just tell the solution quickly. Like, we know that if uh, we will just binary search on the weight. So we will just binary search on the weight, because if we are able to find the weight for which the path exists with less than or equal to d edges, and we know that after adding more weight, still those edges will be there, right? So we know that the function is monotonous again here, because after adding the edge, we still have the old path which was already less than d. So we will just do a simple thing, that if all the, like, we will take mid as the query weight, and we will add all the edges that have weight strictly less than or equal to the query, that is d. Let's say not d, let's say mid. So if there is a path of length less than or equal to d in this graph, then we know that we have to check, we have to decrease the right bound, right? And if there is no path, then we need to increase the left bound. That's it. So for finding the path, we can use BFS, that will give you the shortest length path. And yeah, we will ignore the weights while calculating that path, because we already know that all the weights are less than or equal to the query weight, right? That's it. Any questions so far? If not, I will go on the next topic, that is an interesting one, parallel binary search. Yeah.
So when you have like m roads connecting one to n, I do not know whether we have sufficient roads to reach from one to some given number. Like,
Yeah,
what is
so
it
in that
minus?
case you have to return -1. So um, like, you will do a BFS, right? In BFS, if there is any path, you will eventually end up finding it. If there is no path, you won't find it, so you will return -1 in that case.
I think if we only need to find the path from 1 to n. So if we don't have enough edges in our graph, I think BFS will give a very large value, right? It won't be able to find the path from. Yeah.
No, you will visit each node only once in BFS. So there won't be a loop. There will be at most n iterations. And in this, like, just a minute. Okay. So in this problem, we are just focusing on the number of edges in the path, because we have already eliminated that constraint on weight. So we are just focusing on number of edges. So at most n edges we are going to explore.
So, for example, if we keep doing a BFS and we figure out that at some point we have exceeded two edges, like we just stop with experiment.
Yeah.
Yeah, that makes sense.
Okay, so let's move on to the next topic, and it's an interesting one. It's called parallel binary search. Till now we were just focusing on binary search, like one query at a time. Now let's say let's consider this problem directly, like we'll learn through the problem directly. So there are n cities in Byteland but no roads between them. However, by each day a new road will be built and there will be total of m roads. So there will be m edges, but the catch is one edge will be one road will be built on a single day and the next one will be built on next day. So you have to process q queries of the form after how many days can we travel from city A to city B for the first time. So let's look at the example. There are five edges, five nodes, and four edges will be there. So 1, 2, 3, 4, 5. On day 1, we are building the road 1, 2. On day 2, we are building 2, 3. And day 3, we are building 1, 3. Day 4, we are building 2, 5. And next are the queries. So we want to know, like, when can we travel from 1 to 3 for the first time, 3 to 4 for the first time, and 3 to 5 for the first time. So for 1 to 3, on day 2 itself we have this path, like from 1 to 2 and 2 to 3. On day 2 itself we have a path. The road will be constructed from 1 to 3 on day 3, but the earliest we can travel is day 2. So answer will be 2. For 3, 4, we don't have any path. So I think yeah, we have to return -1 in that case. Like it's never possible. So -1. And 3 to 5. 3 to 5. So here is the path. Here is one of the paths. Like from just a minute. 3. So either we can follow this path, like 3 to 1, 1 to 2 and 2 to 5. It will take, like, the maximum, the last built age is this, so it will take 4 days minimum. And even on the other path, like all other are less than 4 only, and this is connected, 3 and 5 are connected, so it will take 4 days only. So did you understand the problem statement?
Can you explain a bit more about how the input is coming, like where are the edges and where?
Okay, so this is the number of vertices, and then this is the number of edges, and this is the number of queries. So this 4 will be the number of edges. So these are the edges that will be built on day 1, day 2, day 3 and day 4. And the next, that is this 3 will be, last 3 will be the queries.
Okay.
Yeah, so the answer was 2, 1, 2, 1, and 4. So yeah, any approach for this? A naive approach would be like just go day by day, check for day 1 and go for day 1 and mark all the edges that are there with this value of the day on which it was built, right? And among those you can find out a path and will see if it is connected or not, right? That would be a nice solution, and it will take order of, like, you will end up doing BFS or DFS for every day, so it will take m into n time. N vertices are there, and then yeah.
So do we know that the first edge has always to be done on day one?
What? Yeah, we know that these edges are built every single day. Like, yeah, each day a new road is built. Like, the first edge is built on first day, the second one on second day, like that.
So why would that take this complexity? Because then we can just it is just about building the graph, right?
Huh?
Build the graph, you mark the day where the it was done, and that
Sorry? To build the graph
why the
and
complexity? Why is the complexity so high which is making the graph?
yeah, I was talking about the naive solution. So in this solution, what are we going to do? Like for each day, we will see if all of these are built. Which of these is already built? Okay. So for each day, we will do a DFS and we will determine if those are connected, right? So we are going to iterate over all queries every day. So it will be m q into m. Oh, sorry, I wrote something else last time. And yeah,
Yeah, Q into L makes more sense. Q times we have to travel graph for each bit, starting from the day one.
yeah. Oh, sorry. For each day, you have to travel. So it will be q into m into n plus m, right? For each day, you will check each query and you will do a DFS.
Oh, okay, yeah. Yeah, that is my solution there.
Okay?
For each day, we will, I mean, whatever the graph is constructed, we would run the DFS on checking whether the given A and B in the query, can we kind of go via that? Are they connected?
Okay. Now, can you eliminate this m factor from here? Can we try to eliminate this m factor? Can we decrease it somehow by using normal binary search?
One non-binary search idea that comes to my mind is to use maybe a union find kind of a thing where
Yeah.
actually building the graph where keep tracking the first day where certain
Right.
it becomes right?
So in that case, it will be like you will still end up processing or checking all q queries on all m days, but this you are not doing this DFS. You are just doing some order of like some constant time operation that you will insert the edge and you will check if that edge like this query is satisfied, like 1 and 3 are corrected. Is that you are saying?
Yeah, right. That will take few times.
Right? Okay. So now what we have is a data structure for disjoint set union. We'll keep that aside. Like we will use it, but still q into m is 4 into 10 to the power 10. Still it won't pass. Can we decrease it again?
So what if we sort the query?
Huh?
What if we sort the queries according to our ages
Okay.
so that we can keep storing the value of each query and we later union find.
You can keep storing the value of query. I'm not getting how will it help.
The healthcare is done, you won't have to, like, by the time you have completed building the graph, you would have already stored. Okay, no, I see the problem. The problem is that you could try to do that. I'm not sure if it will work, but the idea was that, like, if we sort the queries according to the edges, like in the relative order of the edges,
But
In the
how are you
course
going
of
to sort the
practice,
queries
you don't.
in the order of pages? Like,
You don't have to come back again and look at the query.
uh, how can you do that? I'm not sure.
So, like, are you saying that 1, 3, the part of query, the first query 1, 3, we will kind of take it after the edge 1, 3 is there on the graph. Is that what you are saying?
But I don't know, like it's just an idea, I'm not sure. I think in the interest of time, we should go finally.
Yeah, I will also thinking. Not sure how
The way
that will be.
I'm still skeptical about this given to M. That's it needs more introspection. Like for each query, we are checking each day, right? Hello.
Yeah. In this q times m times o of 1, yeah, this solution take for each query, we will kind of process the graph as it is, like as it was given, and check the connected. But then not sure how to plug and this.
Actually, I'm skeptical about this. Should be more, even if we do that. We do takes order of m. We can just say it takes order of m time to process all the edges in DSU. Okay, it will work in Q into n. Yeah. How we can use binary search here? Can we somehow eliminate n? Or Q, anything? Let's say so what will be the answer for query? It will be some day, right? And if we know that the answer exists for a day, then it should exist for, like, that will be, like, if there is a path on day m, day I, then that path will be there on day I plus 1 also, right? So we can binary search the day for each query, right?
Okay, but what would be the
What will be the time complexity for that? This will change, right? For each query, we will do log m, like we will do a binary search, but we will end up like order of b plus e, that is n plus m in DSU, doing this in DSU. So it actually worsened our problem. But what parallel binary search will help us achieve is, we'll end up making this queue to log queue. So interesting, right?
yeah, no. How do we do this?
Okay. So
Okay.
how are we going to do it is, like, when we are querying, we will check all the queries, sorry, we'll check all the queries at the same time. Okay, do you want to understand through the code? directly because we are running out of time. So what we are going to do is, first of all, if the query elements are same, so I'll just explain the short forms that I have used. So these are the edges, and the first element and second element are the nodes there. Okay, and yeah, so okay, we are taking in the edges, and for each edge, if like those elements are already same, the nodes are already same, then we are marking the answer as 0, answer for that query as 0, and we are just keeping a track that this query is solved. Okay, we will just keep a track for each query if it is solved, and we will, so we wanted to do a binary search for each query. So for each query there will be some left and right bound, so we are also going to store them. So this is for storing the left and right bound for each query, and this is for storing the answer for each query. And yeah, this will store the queries. It's a pair of long names. Okay, and yeah, we are taking the edges here. Taking the edges here, and for each query, if the query sorry, the query nodes are same, then we are setting it to done, and otherwise we are setting the answer to -1, because we assume that there is no path, there is never a path, and we know that we are at most going to do m iterations because there are only m edges. So we will set the left and right bound of all the queries to 1 and m respectively, and so we are going to do a binary search, right? So binary search will take at most log n operations. So we are going to do log n operation, log n times we are going to iterate, because in that time we will end up processing all the binary search operations, right? So we'll iterate for log n times, and I've just increased it by 5 to like eliminate the edge cases. Since it's monotonous, it doesn't affect, right? So yeah, as we were talking, like we will maintain a disjoint set union, and okay, here is the first point that we are going to do. So we have stored the left and right indices for each query separately. So we are going to iterate over all the queries. We are going to iterate over all the queries and check if the left means the binary search condition has violated, and if it is not already solved, right? If it is violated, if it is not already solved and the condition is violated, then we know that this is not going to happen, this is not going to be connected at all. So we'll just mark done as 1, and we have already set answer to -1. But if the condition is satisfied that the left bound is less than the right bound, then we will just add for that query the current mid. The mid will be left plus right by 2, as we always calculate, right? So for each query we have the time, the mid that we have pushed in the list vector, right? Now for each edge we will add the edges one by one, right? So we have added this ith edge, and at this time, like for this time, we will see if we had the mid as the solution, the mid at that time for any query, and if it was the case, then it would be pushed in this vector corresponding to I. So we will just check if that query which was pushed in this vector, if it is solved, we will just see if those edges corresponding to that query are connected. If they are connected, then we will set the answer and move the right boundary. So I always use this overwriting thing for the binary search problems. So yeah, we will just mark the answer and move the right boundary, because we know that it is connected till this time. So let's check if it's connected even before that, and otherwise it's not connected currently. So we'll see if it's connected later. So we'll update the left of that query, right? And how much time does it take? This will take order of n, and yeah, this is taking order of q. So m plus q. Sorry. So this loop is taking q. This loop is taking m, and yeah, we are doing it for log q times. This will be the time complexity finally. Any questions?
How many elements in that list can be present? Like, why are we using that it's off at the line 122?
Line 120. Oh, okay.
So this might not be constant.
So yeah, there we are taking the amortized analysis here. So what are we doing is, for each query we are pushing the mid corresponding to that. So for each query only one element is pushed, right? So total size of list overall, that is sum of list I over all I, is equal to q, right? So
Yeah.
overall time by this will be m plus q. Okay, so it will be 2q. Okay.
And why do we know this, that it will get correctly finished in the log of query size plus log query size? Like, why are we assuming that till why are we running this loop only till t?
Okay. Are we
I
running
mean,
it till t? So
like log q.
actually I think it's wrong.
This,
Should be
we
run
know the
till
answer for
log. Yeah, it's wrong. Should have run till log m plus q, because m is the answer that we are trying to find, right? Like the upper bound of answer. It should be log n plus q. Yeah, we test cases. Yeah, it should be log m. It was a mistake. Any other questions?
Can you share the problem links for this, like to solve from that?
got the gist of it, right? Like for each query, we are just storing the left and right index at every point, and we are marking if any query is already done or not. And we are also like setting the iterations, the number of iterations to the log of answer, that the log of maximum that is possible. And then we are basically binary searching over the answer only, but we are doing it for every query in each iteration of the answer, like, of the binary search. So it's parallel binary search. Any more questions? If not, you can end the session. The plan tasks are done. So do I have the permission to end this meeting? Comment. Yeah, okay. Thank you for joining everyone, and yeah, it was nice talking to you. You're welcome.